Hey guys, so today we are going to talk about accelerated frames of reference and how to solve a problem in an accelerated frame. There are some problems in which this method is going to prove to be much easier than solving the problem in an inertial frame. We are going to use a method which we call Einstein's method because it comes from Einstein's idea. So first, let me explain Einstein's idea. Supposing there is a frame of reference which we'll call S. This is a coordinate system which I have set up in an inertial frame which we call S. And let's say we have an accelerating frame, and this accelerating frame we'll call it S prime. Now we are going to define first the position vector of the origin of this S prime frame as seen from S. We're going to call this position vector R, and let's give it a subscript F standing for frame, accelerating frame. I'm doing a little bit of theory to explain Einstein's idea. So this is RF. Now two people, one person who is observing the world from an inertial frame S, another person who is observing the world from an accelerated frame. Maybe she is sitting in an accelerating car or a train or in an accelerating elevator, it doesn't matter. Both are looking at the world, and let's say both of them look at a bird. Now, the person in the inertial frame will claim that the bird's position vector is this, which we will call R. The person in the accelerating frame will see the bird's position vector as this vector, and she will call it R prime. Everything observed in the accelerating frame we will write with a prime. Now if you look at this triangle, you can easily see by vector addition that R is equal to R frame plus R prime. Now as the bird moves and as the accelerating frame moves, R changes, R prime changes, RF changes, but this relationship will hold at all times. So all three are functions of time, so we can differentiate them with respect to time. So if I differentiate this equation, I get the velocity of the bird as seen from the inertial frame is equal to the velocity of the moving frame plus the velocity of the bird as seen from the moving frame. This is the velocity transformation equation that we use to solve the direction of rain problems, river and boat problems, aeroplane and wind problems. Since we are now talking about accelerating frames, let's differentiate it again. Remember, these are also functions of time. So if I differentiate it, I get the acceleration of the bird as seen from the inertial frame is the acceleration of the accelerating frame itself plus the acceleration of the bird as seen in the accelerating frame. That is, if the accelerating frame is an accelerating elevator, A prime is the acceleration of any object seen from this elevator. A is the acceleration of the same object as seen from the ground, if we take the ground as the inertial frame. Now we know that in the ground frame, this is true. The net force on the bird or whatever object we are looking at is equal to its mass times its acceleration. So the net force on the bird or whatever object we are looking at might consist of the force of gravity also on the bird. So we will write it as mg. G is the acceleration due to gravity. In this case, it is downwards, plus all the other forces acting on this object, which we will call F1. That is equal to mass times acceleration. For acceleration, we can now substitute acceleration of the frame plus acceleration A prime. Now here's the important thing. On the left side, we have the total force acting on the bird. That is the same in all frames of reference. Think about it. The net force acting on the bird is not equal to mass times A prime. In other words, in the accelerating frame, if Newton's law held, we would get the equation net force left hand side is equal to mass times A prime. But that's not true. There is this AF sitting in between. That means Newton's second law doesn't hold in the accelerating frame. So Einstein's trick is take this MAF to the left side. So we write it as M G minus AF plus all the other forces, for example, air friction, whatever else force is acting on the bird, F1 is equal to M A prime. In other words, now we can go ahead and apply Newton's laws in this accelerated frame. Writing the net force on the bird is equal to mass times acceleration in this frame, provided we change the gravitational field like this. So all we have to do, if you are in an accelerated frame, is change the existing gravitational field by adding an extra minus AF, an extra acceleration due to gravity, minus AF, as though somebody had turned on an extra gravitational field. For example, if the elevator is accelerating downwards, you add an extra gravitational field upwards to the existing gravitational field. If the elevator is accelerating upwards with an acceleration AF, to the existing gravitational field, you add an extra gravitational field pointing downwards of AF. G is already downwards, so the magnitude becomes G plus AF. Now normally, people call this minus MAF a pseudo force. Now we are not going to use pseudo forces. We are going to use Einstein's way of thinking. Einstein's way of thinking is the gravitational field depends on the frame of reference. In an accelerating frame, the gravitational field is different from the inertial frame. And the new gravitational field is G minus AF, where AF is the acceleration of the frame, the accelerating frame. All you have to do is change gravity and now go ahead and apply Newton's laws. The total force is equal to mass times acceleration, which means we can now treat this accelerating frame as a stationary frame. This is Einstein's idea. I'm going to repeat this. Please listen carefully. You have an accelerating frame, like a car which has an acceleration AF. Now you can solve every problem from this accelerating frame using the accelerations of all objects as seen from this frame and applying force is equal to mass times acceleration as though it was a stationary frame. All you have to do is change the gravitational field. That's all. If there is a gravitational field G, add to that an extra minus AF. AF is the acceleration of your frame. Let me apply this to some problems and show you how it works. Here is a problem that you might be familiar with. An elevator starts from rest and moves upward with a constant acceleration of 4 meters per second squared. 2 seconds later, a bulb breaks loose from the ceiling. That means when it breaks loose, its upward velocity is 8 meters per second and it's now in free fall. So as it falls, in fact, it moves up and then comes down because its initial velocity is upwards. But as it's moving up, it's slowing down due to gravity because it's in free fall. But the ceiling of the elevator, which also had a velocity of 8 meters per second when the bulb broke loose, the ceiling of the elevator is accelerating upwards, so it always stays above the bulb. So the bulb moves up and comes down. In the meantime, the floor of the elevator catches up with it and the bulb breaks on the floor of the elevator. From the moment that the bulb breaks loose to the moment that it breaks on the floor, what is the time interval? Now, I urge you to solve this problem from this point of view, from the ground point of view. I will now show you how to solve this problem using Einstein's method. Using Einstein's method, we get into the frame of reference of this accelerating elevator. That means, for example, you might be observing this from the point of view of somebody inside the elevator. Now, from the frame of reference of the elevator is stationary. And when the bulb breaks loose, its initial velocity is 0. It's a stationary elevator. Taking down as positive, the displacement is 4 meters until it hits the floor. The only difference is, in this frame of reference, the gravitational field is different. according to Mr. Einstein? There is the usual gravity, 10 meters per second squared downwards. Apart from this, since the elevator has an upward acceleration of 4 meters per second squared, we have to add an extra gravitational field of 4 meters per second squared downwards. So the gravitational field inside the elevator is G prime, which is 10 plus 4, that is equal to 14 meters per second squared. Now it's very important for you to understand this is not just the gravitational field inside the elevator. This is the gravitational field all over the world, even outside the elevator, as seen by somebody who is accelerating upwards at 4 meters per second squared. So in this upward accelerating frame, the gravitational field is different. This is Einstein's beautiful idea. It takes a little while to wrap your head around it, but if you just accept it for now, you will find problem solving becomes very, very easy. Compared to using, pseudo forces and things, this method is not only far superior, it leads to a lot of beautiful physics. All right. So S is equal to 4, taking down as positive, S is equal to ut plus half A, which is 7t squared. So the time of travel for the bulb is going to be square root of 4 by 7 seconds. That's it. Problem solved. You see how simple it is in the accelerating frame if I use Einstein's idea. Let's do another problem. Let me remind you of this famous problem where a gun is aimed at a target which is at a height, and at the instant that the gun is fired, this is released from rest. Now the question was, if you remember, as the object falls down, the bullet also curves due to gravity, and prove that the bullet in fact strikes the target. But imagine doing this problem not in this frame of reference, but in a freely falling frame of reference. That is, the frame of reference itself is falling with an acceleration g. In the freely falling frame of reference, apart from the gravity due to the earth, you have to introduce an extra gravitational field of minus g. They cancel, and in a freely falling frame, there is no gravity. That is, an elevator whose cable is being cut, inside the elevator you feel no gravity. So in a freely falling frame, there is no gravity. If there's no gravity, the target is released and it stays where it is in this frame, and a bullet aimed at the target will also go straight without bending because there is no gravity, and it will hit the target. Finish. That's the proof. Think about this. It's so beautiful when you see it in the frame of reference which is freely falling. All you have to do is change the gravitational field. In a freely falling frame, the gravitational field becomes 0 and the problem becomes extremely simple. Okay, in this problem, what we have is an accelerating vehicle which has a steady acceleration of 4 meters per second squared, and a pendulum, a simple pendulum hanging from its ceiling, makes an angle theta with the vertical under the constant acceleration conditions. Now the question that was asked was, if the pendulum is disturbed, it starts oscillating about this position, and what is the time period of oscillation? The length of the pendulum is given as L. Now, normally what would we do? We would draw a pseudo force and then find the restoring torque due to a pseudo force when it is disturbed by a small angle from equilibrium, and then write down the simple harmonic motion equation. We don't have to do any of that using Einstein's method. How do we use Einstein's method? Well, let's move with this van with the same acceleration. That means we are in an accelerating frame of reference. Perhaps we are looking at it from the point of view of this person inside the van. Whether the person is inside or outside, that's not important. The person is moving with the same acceleration. So from her point of view, apart from the gravity produced by Earth, which is 10 meters per second squared, the acceleration due to gravity in that direction, you have to add an extra gravitational field of minus A. A is the acceleration of the accelerating frame. So I have to add 4 meters per second squared to the left. which means the resulting acceleration due to gravity in this accelerated frame is this vector, resultant of these two. Now, this is 4 and this is 10. So let me write that down. This is 4, that is 10. So the angle theta that the resulting gravitational field makes in the accelerated frame is given by tan theta is equal to 4 by 10. So the gravitational field inside this van is in that direction. So what does the poor pendulum do? It simply hangs in that direction. So the direction in which the pendulum hangs in equilibrium in this frame is tan inverse A by G. A is the acceleration of the frame. We have already solved this problem by using tension and mg and all that several times. So now we see this from Einstein's point of view. But let's go further. Let's now disturb this pendulum and let it oscillate. If it oscillates, now remember, this accelerating frame of reference can be treated as a stationary frame provided I change the gravitational acceleration, the gravitational field, to G prime. And what is G prime? This is G prime. You can see G prime is going to be equal to square root of 4 squared plus 10 squared. That is equal to 100 plus 16, 116 square root of meters per second squared. That's it. What's the time period of the pendulum? T prime, which is the time period in the accelerating frame, is going to be equal to 2 pi root of L by G prime. Take this G prime and put it in here and the problem is solved. What Einstein is telling us is the gravitational field that you see depends on your frame of reference, just like the velocity of an object depends on the frame of reference. Coming back to this problem, let me tell you a few more things. Now in this frame, gravity is in that direction, so this person will actually be standing comfortably at that angle. If he tries to stand like this, as it's drawn in the white, he will tip over. So he has to lean forward so as not to fall. And one more thing. What if this vehicle contained a lot of water on its floor? The water will accumulate towards the back side, right? And this will be the water. And if I ask what is the angle that the surface of the water makes with the horizontal, you can easily find out, because the surface of the water will be perpendicular to the gravitational field. So if this gravitational field makes an angle theta with the vertical, the water surface will make the same angle theta with the horizontal. Think about it. You see, so many beautiful things can be concluded from this idea of changing gravitational field.